So, in the last class we talked about the capacitor and the effect of dielectric in the capacitor. So, we will continue that in today's class, and we will see some more situation where there is a dielectric inside capacitor. Let us start. So, let us see one simple example. We have got two materials between plates of capacitor. So, here we have one plate, this is another one, and in between these two plates of capacitor we have two material, one is dielectric, another is conductor, right, and you have to plot electric field versus x and potential versus x curve for this situation. So, if I assume this to be x is equal to 0, right. So, this I am assuming x is equal to 0. How field is varying with x, that I need to plot. So, if I assume the charge here is plus q and the charge coming here is minus q, what would be the field here at this particular point? As we know, there is no effect of the induced charge here at external point. Similarly, there is no effect of these induced charges at this particular point, because whatever the positive charge here producing field, the negative charge will produce field in opposite direction. So, the effect of induced charges on the surfaces of dielectric and conductor, they do not have any effect at outside point. So, here I can directly write field because of this positive charge q upon 2 epsilon naught and because of this negative charge q upon 2 epsilon naught. So, net field at this particular point or in this region, that will be q upon a epsilon naught, right. And we know that whatever be the field outside, inside dielectric field will become by k times, right. So, here field inside dielectric, if I want to write field here, then it will be q upon a epsilon naught divided by k, because outside field is q upon a epsilon naught, right. Again at this particular point, this and this they will produce field q upon a epsilon naught. So, here field is q upon a epsilon naught, right. Inside conductor, because for conductor we have dielectric constant infinity. So, here if I write k and k is equal to infinity, this value will become 0. So, field here will be 0, right. Similarly, whatever field here, same as field here, same as field here. So, here again field is q upon a epsilon naught. So, this is the way we will be having field. If I want to plot it, obviously by k I am writing, so k will be greater than 1 or equal to 1, here dielectric I am using k will be greater than 1, then the field here will be something less than whatever be outside. So, here whatever be the field there, by k is the field inside the dielectric, right. So, if I draw, I will get something like this. So, if this field I call E naught, here I am getting E naught, inside dielectric I am getting E naught by k, right. So, this up to dielectric over. Now, when I cross dielectric, I come out of the dielectric, then again field become E naught, field here again become E naught, this value is E naught. When I go inside conductor, then field here becomes 0, inside conductor there is no field, no electric field under electrostatic condition, so field will be 0. Now, when I come out of conductor, then again I have field, this field, that is E naught. So, field here also E naught. This is the way field is there in a space, right. If I want to draw electric field lines, it will be something like this, from positive to negative, something like this. Here intensity is more, as I go inside intensity will be less, I am denoting it by less number of lines, right. And then as I go out, again I am going to get the same number of line, it will be something like this, right? And inside conductor there won't be any line, there won't be any field, and when I come out of the conductor again I am going to get the same field. So same number of line as I have drawn here, I will draw the same number of line here, right. So this is the way there will be field in a space, and this is the variation we have plotted. Now for potential, if I consider this as a reference, some positive potential, right, we know that dV is equal to minus E dot dr, right. As field in different region is constant, throughout the region field is constant, if this is constant, you can see that if I put limit that x is equal to 0, I will be on this plate, potential is some V plus, and what would be the potential when I go by some distance x, let that be V. So if I send minus sign this side, I am getting V plus minus V minus is equal to field, whatever I am getting in this region, I am getting E naught into x integration of this one. So you can see that you are getting a positive, you can see that you are getting for V, focus on V, I will write it again. So we are getting V is equal to, so put the minus sign here, E naught x, and this goes this side, this will be plus V plus. So we are getting equation of a straight line with negative slope, right. When I go into dielectric, the slope will become E naught by k, slope gets reduced. Then here in this region again I am going to get the same expression for slope. Here I am getting slope 0 because E itself is 0, right, and here again I am getting the same expression. So if I plot this, I am getting a straight line which is having slope and positive y intercept. So it will be something like this. So if I start from positive, I am assuming this to be V naught, right. So from V naught I go to this one, potential decreases as I am going along the field, and then suddenly there is change in the slope. So slope of this line is different to slope of this line, right. And then when I cross this one, again I will be in the region where field is same as the previous one, E naught. So slope of this line will be same as slope of this line. So these two will have same slope, and here slope will be something less. Now when I enter into conductor, whole conductor will be at the same potential because field is 0. So every point on the conductor will be at same potential. So potential is not changing, that is why we have a line parallel to x axis, slope is 0, right. Then I enter into this region where again field is there, along the field potential decreases, and you will be getting this line. So this line and this line, this region and this region, they have same field, and these line will have same slope. So this is the way we plot potential versus position curve using the field versus position curve, right. So I hope this example is clear. Now let us move to next one. So inside capacitor we can arrange dielectric in n number of ways. The most commonly used ways might be like this. We have one dielectric base this way, and the next one is having same area placed beneath this one. And the second way of doing it, like instead of placing one over another, we can place side by side. What difference does it make? If you look at the first one, then it is something like this capacitor and this capacitor will have this surface common. So I can draw it this way, one capacitor here which is representing this one, another capacitor here which is representing this one, right, and it is filled with dielectric, one air, another air, right. So, this is the way I can see this capacitor, right. While in second situation, if you see that for this capacitor, for this whole capacitor, first terminal is connected to first terminal of this capacitor. These two are connected, they are at the same potential made by same sheet, right. Similarly, the second terminal of this first capacitor and second terminal of second capacitor, they are also connected because they are made up of same plate, right. So, these two are at the same potential, these two are in same potential. I can see this as two capacitors connected in parallel, right. So, this is the way I can see. Right. So, here I can see this as series combination and this one as parallel combination, and if I want to write capacitance, see, series combination formula is what? C1 C2 upon C1 plus C2, while in this situation I need to use parallel combination formula, that is C1 plus C2. So, what I will do, I will calculate the capacitance of this part, that is C1 I will write here, similarly C2 of this part I will write here. Series combination formula I can use for this arrangement, C1 C2 upon C1 plus C2. While in second case, these two are in parallel combination C1 plus C2. So, this capacitance I will calculate and this capacitance I will calculate and I will add them, I will get C equivalent for the arrangement. So, I hope this concept is clear. Based on this concept, there are so many questions came in JEE. Let us see one. So, now I have arranged 3 dielectric this way, right, and I need to find out the capacitance. So, when nothing was placed, the capacitance of the arrangement was C, it is given, and then we place dielectric slabs this way, and now I want to find out the capacitance of the arrangement. Now see, you can treat this as one capacitor, you can treat this as one capacitor and this as one capacitor, and they are connected in parallel. I hope diagram is clear. So, these two, they are connected in series. So, this one they are connected in series, then they are connected in parallel with third one. So, I can see this as one capacitor over here, one capacitor over here, and then one here and one here, and then they are connected in parallel with third capacitor, right. So, one here, another here, okay. This is the way I can visualize this diagram, right. So, some student, they commit mistake in visualizing this whole arrangement as this capacitor see. What they generally do, they draw it this way. This is the most common mistake student commit in exam. This means that half of this and this K2 and half of this K3, they are behaving as parallel capacitor, then the remaining half is in parallel with K1 according to this diagram, right. But this is wrong. Why this is wrong? Because we are not getting potential here same as the potential here. We cannot say that this part and half of this part, they are at the same potential. If you draw this diagram, you are saying that potential at half of this one and the potential till here, they are same, then only they can be in parallel combination, but they may same or they may not be same. The only thing we can say is the potential of this and potential of this, they are same, and potential here, because this is single plate, potential here is same as potential here. So only thing I can say that this and this, they are at same potential, and this they are at same potential. This diagram says like this plate and this plate, they are at the same potential, and this plate and this plate, they are at same potential. But this is saying that middle of this one and this one, they are at same potential, right. I hope this is clear why we are drawing this way, right. So this one is wrong. So careful while visualizing capacitor when there are multiple dielectric placed inside. Now only thing we have to do, we have to just simplify, right. So if I just remove dielectric for time being and I ask what is the capacitance of the arrangement, right. What is the capacitance of this one? If the whole one is having capacitance C, that means without dielectric if whole thing is having capacitance C, that means epsilon naught A by D is C, right. So this C I am talking about, right, this C I am talking about. When there is no dielectric, capacitance was epsilon naught A by D. Now, so without dielectric, what would be the capacitance of this one? Area has become half, separation is D. So for this capacitor, I will write epsilon naught A by 2 divided by D, that is nothing but C by 2. So capacitance of this empty space arrangement is C by 2. Now look at this one, this part I am talking about without dielectric. Area is half and separation is also half, D by 2 and D by 2, right. So only for this part the capacitance is epsilon naught A by 2 divided by D by 2. If I simplify, this will become C. Same thing happens to the below one is also having capacitance C, right. So without dielectric if I draw it again, it will be something like this. This part will have capacitance C by 2 and this part will have capacitance C, this part is having capacitance C. But with dielectric, if I place dielectric here, so the capacitance now will become, if dielectric is placed of dielectric constant K, then capacitance will be K times this. So here I am placing K3 is having dielectric constant 4. So here it will become 4 C by 2. I hope it is clear. Now for this one I am placing K2 is 6. So here capacitance will become 6C, right, after placing dielectric 6C. Now the below one, K1 is 3, right. So this is 3. So what I will do? 3. So this will be 3 C. So now after filling it, the capacitance of this one will become 2C, right. So here I am writing 2C with dielectric, right, and here I am writing 6C, and here I am writing 3C. Now as you can see, these two are connected in series. So C1 C2 upon C1 plus C2. So for this arrangement I am writing C1 C2 upon C1 plus C2, that is coming 3C, right. So the whole thing is representing 2C. By 6 into 3 will become 18. 18 divided by 9 will give you 2. So this will be 2C, right. So here this branch can be replaced by a single capacitor of capacitance 2C, and this is again 2C. They are connected in parallel. What would be the capacitance? So equivalent capacitance will be 4C. So when there are multiple slabs, you have to be little careful, because a small mistake will lead to wrong answer. I hope this concept is clear. So before considering something in series or parallel, you have to see which all surfaces are having same potential or not, right. So same potential surfaces can be drawn this way, and after simplification you will get the result. So filling is clear. Now in this situation we have taken isotropic dielectric, whose dielectric constant is same everywhere. You may be given a situation where the dielectric constant varies with distance. So dielectric constant is not uniform. For example, look at this example. Here dielectric constant varies with distance. So between two plates of capacitor, we have placed a dielectric whose dielectric constant varies with distance x, where x is from one end. So from here at distance x, what would be the dielectric constant of a small slab if I take? So it varies according to this relation, and you are asked to find out the capacitance of this arrangement. Okay. So calculate the capacitance. Distance from left end is x. So capacitance. If I take a small element of dielectric at distance x, this way, at distance x I have taken a small slab of thickness dx, what would be the capacitance of this arrangement? We can do one thing. So there is a plate, I hope you can visualize, right, this way there is a plate and its projection so visualize this plate, and here I can see very small part over the plate, right. So if area of the plate is capital A, or I can say there is square plate, this distance is A and this distance is also A. So, this distance what I am drawing here, this is small a, right, and this thickness as you can see that this is dx, right, dx. So, what I can see is I can see this. Now, what is the capacitance of this part? Capacitance of this part. So, DC is equal to epsilon naught K times epsilon naught area of this surface area of the plate, which is forming capacitance. So, this side is A, this side is A, this thickness is dx. So, surface area will be A dx, right, A dx, divide by this separation d. Okay. So, capacitance of this part is this one. Now, I hope it is clear. I will erase the diagram. As you can see that upper plate of all these such capacitors, they are at the same potential, you can see they all are connected, right. So, they all are connected, the upper part is at the same potential. Similarly, you can see all lower parts, they are at the same potential because they are connected by same plate. So, they are connected by same plate here, they are connected by same place here, plate here. I can visualize this as all DCs, DC, all DCs are in parallel combination, right. So, parallel combination, I just need to add capacitance C1 plus C2 plus C3 like that, right. So, while in this situation as dielectric constant is varying continuously, I can integrate. So, I can use integration to add all DCs, right. So, DC what I am writing is DC is equal to, in place of K I can write K naught 1 plus alpha x A dx divided by d, right. If I want to add all DCs, I need to integrate. So, if I integrate, limit will be 0 to A, So, I will put the limit 0 to A and I integrate this term. Integration of first term dx, if I multiply it will become x, 0 to A it will give you A, and then second term is x, if I integrate with respect to dx it will become x square by 2, upper limit minus lower limit, A square by 2. If I simplify, I will get this one. So, the dielectric we are using, that is not same throughout. As it was not same throughout, we considered a small part of the arrangement, we calculated its capacitance. As from the diagram I got information that all DCs are connected in parallel, and for parallel plate we have formula C1 plus C2 plus C3, we just need to add all capacitance. I am just integrating this expression, right. I hope it is clear. So, after integration you got the capacitance. If this is the way capacitance varying, I could have given this dielectric constant varying according to y. So, let us see what we need to do then. If So, let us first erase this part. Now, what I am saying is, instead of k varying with x, if I give you a situation where k varies with y, I say this is y and we are getting k is equal to k naught 1 plus alpha y, right. Now, you can see as k varies with y, I need to consider slab this way, I will consider slab this way. And now what I see, in previous case slabs were like this, I added all DC to get total capacitance. In this situation, all the slabs will be like this. So, there in this situation, all the slabs are in series combination, charge will flow like this. So, all DCs are in series combination. What I will write? First I will write DC, DC is equal to epsilon naught k times surface area will be A square only, right. The thickness of this one will be dy, so I will write dy here, divide by dy. This will be DC, and for for series combination we know that 1 upon C equivalent is equal to 1 upon C1 plus 1 upon C2 like this. That means you have to get 1 upon DC and then you have to add. So, in this situation I have to integrate 1 upon DC to get C equivalent. So, 1 upon DC is dy k epsilon naught A square, that I need to integrate. Substitute value of k, we know k in terms of y, it is given in the expression k naught alpha y, k naught plus alpha y. A square epsilon naught out and A square limit, right. Limit is 0 to d, limit is 0 to d. So, here limit will be 0 to d, and do remember after integration you are going to get 1 upon C equivalent, not C equivalent, 1 upon C equivalent. So, integration of this term will give you log, right. So, I will simplify it first. So, integration of this term, I will erase this part, all were in series, while adding, as all were in series, 1 upon C equivalent is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. That means we now need to integrate 1 upon DC, right. So, 1 upon DC, substitute the value of k here and then you will be getting in this form, and that we can easily integrate 1 upon epsilon naught A square is common, and then integration of this one, alpha will come in denominator, ln k naught plus alpha y is equal to 1 upon C equivalent, once we put the limit 0 to d. When you substitute limit 0 to d, then you are going to get, now I will remove this one and I am directly writing limit. Here you will get d in place of y, So, in place of y, d will come divide by k naught. This is 1 upon C equivalent, do remember, right. So, what we have learned, that when dielectric was varying this way, then all DCs were in parallel combination. We just integrated DC to get C equivalent. But if dielectric constant is varying this way, then I can see all such capacitors, they will be in series combination, and if we apply series combination formula, then we need to integrate 1 upon DC, and after integrating 1 upon DC, we are getting this result. So, I hope you are able to visualize in different situation how dielectric is playing important role and how plates are playing important role to decide whether they are in series combination or parallel combination. So, whole concept is clear. Let us move to next example. Now, see, look at this one. So, if instead of placing dielectric, this way I am placing the upper dielectric making some angle and lower dielectric is making some angle. It is in the form of triangular wedge. This is also in the form of triangular wedge, and they completely occupy the space between two plates of capacitor, and I want to find out equivalent capacitor. Now, here you have to be careful while analyzing what you need to do to add capacitance of a small part. So, we will use the concept what we have just discussed. From here at distance x, if I take a small element, this one, right, okay, see this way, this thickness is dx, and upper one I will draw by some other color so that you can see the difference. So, you can see there are two capacitors, right. In DC itself there are two capacitors, lower one and upper one. If lower one I call DC1 and upper one I call DC2, lower one up to here DC1 and this is DC2. Let this height be y, this remaining is d minus y. So, as charge goes this way, this capacitor both will be in series combination, right, and we will apply series combination formula. DC for this small element I am getting DC1 into DC2 divided by DC1 plus DC2, because these two are connected in series, right. So, let us substitute the value and let this angle be theta. So, I can write tan theta is equal to this is d and this one say a. So, tan theta is equal to d by a, which is equal to, look at this triangle, this is x, this is y by x. So, here I have relation between y and x, right, because this whole thing is constant, I can multiply it over here. Now, DC1, look at this capacitor. If this is square plate, this one is square plate of A cross A. Square plate of A cross A. So, this is A, and this is also A. So, the strip I can see over the plate is this one. Right, this is strip, focus on this strip, this is A and this thickness is dx. So area of this plate will be A dx. So capacitance is epsilon naught A area A dx by d. I am writing for this one, for d for this one is y, okay, and into K1 dielectric constant. So dc1 over, similarly I can write dc2, this will be K2 epsilon naught A dx divided by d minus y whole divided by, this you need to add. So K1 epsilon naught A dx divided by y plus K2 epsilon naught A dx divided by d minus y, right. This is dc, this is dc, right. If I simplify this y and this will get cancelled out, and here we are left with, if I just want to simplify the whole expression, so 1 epsilon naught A, that will get cancelled out. So here we are left with K1 K2 and only 1 epsilon naught A will be there, and this is dx and 1 dx will get cancelled out. So you are going to get only dx over here, then divide by d minus y K1 epsilon naught A dx, right, dx got cancelled out. So the dx, 1 dx got cancelled out by dx appearing in numerator. Y K2 epsilon naught A dx, again dx, 1 dx got cancelled out. So now the main concept, all such DCs, this DC, adjacent DC and all these DCs, they are connected in parallel, upper is connected with upper and lower is connected with lower. So as all are connected in parallel, I need to integrate this expression, I need to add all DCs. Here there are two variables involved, one is y, another is x, and we know the relation between y and x. Y is equal to x small d by a, that I can substitute here. So y you are going to get in the form of x, and this whole thing is coming in the form of dx divided by x format, that means we are going to get log. You can simplify. Now limit will be from here at distance x we wrote dc, so limit will be 0 to a. So here I will add 0 to a. So this when I simplify, I will get the result, right. So after simplification we are going to get this as C equivalent, C K1 K2 divided by K2 minus K1, where C is epsilon naught A by D, A is nothing but small a square. So previous cases it was very simple, upper segment and lower segment behaving as capacitor, two were in series combination, we directly added. But here the thickness different segments are having, they are not same. So I will take a small part of the whole arrangement and I will write capacitance of that small part, and as all such small parts they are connected in parallel, I can integrate and I will get the capacitance. So this concept is clear. Let us move to next one. Now let us see some example where we are just adding or we are just removing dielectric in the circuit. So here question says ki we have got one parallel plate capacitor of capacitance 100 microfarad, and it was initially connected with supply 200 volt, right. So this was the initial arrangement, and now what we are doing, we are inserting dielectric constant into the gap between the plate. So here I am adding dielectric. So I will draw another circuit so that we can compare. So I added or I inserted one dielectric of dielectric constant 5 between two plates, right. Before introducing dielectric, what was the charge on the capacitor? Q is equal to CV. Q is equal to CV. Capacitance 100 microfarad into, so we are getting 20 millicoulomb. This much charge was there on the capacitor earlier, plus 20 millicoulomb. Now when you add dielectric, the capacitance, this capacitance will become K times, and K is 5. So now the capacitance of the arrangement will be K times C, and the charge, this is the charge initial. So charge final will become how much? Capacitance, new capacitance is Kc multiplied to V, and now we multiply 5 to this one, I will directly get 100 millicoulomb. So the extra charge given by see the extra charge, this is extra charge. Initially capacitor was having 20 millicoulomb, and finally capacitance got, this capacitor got 100 millicoulomb. That means the extra that is flowing in is 100 minus 20 will give you 80 millicoulomb. So the extra charge that comes into system is 80 millicoulomb, and if I ask how much is the extra charge flowing through the power supply and the work done by the supply, extra charge we got. Now we want to calculate work done by supply. So work done by supply, work done by cell, extra charge delivered into potential difference. Extra charge delivered, how much we are getting is 80 millicoulomb. So 80 millicoulomb into 10 to the power minus 3 into potential difference, if I multiply, potential difference is 200, right, 200 volt. So what we are getting, this is coulomb, this is volt, what we are getting 16 joule. So battery will do additional work which is equal to 16 joule, right. Now out of that, how much energy is stored in the form of field, right. Find the change in the electrostatic energy. Change in electrostatic, how to calculate change? Final minus initial. So you need to write change in energy stored final minus energy stored initial, right. final energy stored half q square by c, right, half q square by c. So, q final you have, q final is finally charge on the capacitor is 100 millicoulomb. So, q square by c, final capacitance is 500 microfarad. So, 500 microfarad, right. So, into 10 to the power minus 6, and this charge was millicoulomb. So, into 10 to the power minus 3 whole square, 10 to the minus 6, right, minus initially the charge on capacitor was 20 millicoulomb. Here I can write 20 into 10 to the power minus 3 whole square divided by capacitance. Earlier capacitance was 100 microfarad. So, 100 into 10 to the power minus 6. I can subtract these two, and after simplification I will get this value as 8 joule. You can check that, right. So, this is an example when we disturb the equilibrium of the circuit. When you just add dielectric, capacitance of the arrangement will get changed. To adjust to new change, cell will deliver extra charge to maintain the equilibrium. So, this much extra amount of charge will appear on the capacitor, and then there is no further flow of charge, because this whole arrangement will acquire the state of, or this will acquire steady state, right. And in that process, how much would be the work done by cell, how much is the change in energy, change in internal energy, how much is the heat. For example, in this situation I ask how much is the heat generated. So, you know the formula for heat generated, you can apply and you can find out the heat generated also, right. So, these 2 points are clear. Let us move to next one. Now, see, alternative form of Gauss law. So, we have seen that when placed in front of plate dielectric, if this one is positive, this side it is positive, then charge appearing here will be negative, this will be minus Qp, and same thing happens here, it will be plus Qp, and the charge appearing here will be minus, and we know the relation, right. So, Qp magnitude wise we got Q in bracket 1 minus 1 upon K, right. If I want to write a field, or if I want to apply Gauss law in this region, total charge enclosed E divided by total charge, or E dot ds is equal to Q in upon epsilon naught. So, the total charge enclosed here, see, look at this and this one. So, here this is Q and this one is Qp with negative sign. So, total charge enclosed here will be Q plus in bracket minus Qp. So, Q total, Q in I will write, that is Q plus minus Qp. Right, and I want to apply Gauss law. What is Gauss law? E dot ds close, E dot ds close is equal to Q minus Qp divided by epsilon naught. So, I will substitute the value of Qp here. So, when I substitute the value of Qp, so this side it will become 1 upon epsilon naught Q minus Qp. If I simplify this, this will be Q divided by epsilon naught K, right. So, this whole thing I can multiply K here, but in that case this charge is not the total charge, right. If I just multiply K over here, this will become K field dot ds is equal to 1 upon epsilon naught this Q. Look at this one, this Q is the charge coming on the inner surface of the plate, right, and that I can also call free charge because it can move. This QP is not the free charge, QP is bounded charge, it cannot move freely because it is on dielectric insulator, right. So, this charge is not moving, this is called bound charge and this is called free charge. So, when you want to write the expression E dot ds close, then this side you have to write total charge divided by epsilon naught, right. But when you are writing this way, k times E dot ds, do remember that here you need to write q free charge divided by epsilon naught, right. So, this is called alternative form of Gauss law, right, but we need to substitute free charge here, then this will be k times E. If you are just writing E dot ds, then this side you have to write the total charge, whether it is bounded or unbounded, the total charge should be written this side. So, this is called alternative form of Gauss law. I hope concept is clear. So, be careful while applying this Gauss law when dielectrics are involved, right. So, best thing you can remember is when you are writing E dot ds, write the total charge, whether it is free charge or bounded charge, you can write it this way, okay. So, alternative form of Gauss law is clear. Let us move to next topic. When I place dielectric inside capacitor or when I just look at the capacitor, generally we draw field lines this way. So, here there will be positive charge, here there will be negative charge, right, and there will be electric field lines in between, we draw them this way. So, this is the ideal situation where we are drawing lines this way, right. But actually what happens that due to the charge at edge, the field lines will bend at edges. So, field lines will be something like this side as well as on other side. So, field pattern in space will be this way. Instead of having a uniform field here, there will be lines outside the capacitor also. This is called fringe effect. So, because of fringe effect, line will bend at the edges, or bending of line at edges is called fringe effect, okay. Now, what this has to do with the force on the dielectric slab what I am placing inside. So, say this is the slab placed inside two plates of capacitor, and as you can see here there will be positive charge and here we got negative charge, and over dielectric here there will be induced charge, right. So, this will be negative, so minus, it will be like this. Similarly, here there will be positive charge this way. So, these I hope you can see, these are positive and this side negative. Now, what happens when there is a fringe effect? So, here the line will be this way, no problem. See here these lines. Now, because of these lines, the charge, what negative charge is here, that charge will be experiencing force opposite to the field, and the positive charge what I am drawing here that will experience the force along the field. So, on this negative charge, the force will be opposite to the field, field is in this direction, force on this one will be like this, and the force on the charge very near to edge, that will be, as field here is in this direction, force will be along the direction of field. So, you can see that there is net force coming towards the gap. So, its component in this direction and this component in this direction will try to pull the slab into the gap, right. So, slab experiences force, slab experiences force towards the gap, right. So, if you release this slab, this will go inside and there is net force towards the gap, right. But if it is well inside, if the plate is well inside, say, or slab is well inside, not plate, if slab is well inside, situation is something like this. So, as you can see that at both the corner here, because of fringe effect, force here will be this way, along the field force will be like this, and same thing happen on other side, that force here will be like this and force here will be like this, force here will be like this, and you can see that the effect from this side and effect from this side, they are cancelling each other and it will stay in equilibrium. But if you slightly disturb it and pull it either this side or pull it this side, then it starts experiencing net force towards the gap, and this force will accelerate the slab into the gap, right. Here we want to find out this force, what would be this force, and we know that force is, if we can calculate the potential energy, we differentiate potential energy with respect to position, then we will get force. So, if we can calculate the potential energy associated, we can easily calculate force, right. So, I hope whole concept is clear. At the edge, field lines will bend, this is called fringe effect. Because of fringe effect, here at the opening or here at the opening, the slab start experiencing force towards the gap. If it is well inside, then the force coming from this side and force coming from this side getting cancelled out, it is not experiencing any net force in this direction, right. But if it is not placed symmetrically, if it is something like this, force coming from this side is not balanced and that resultant will pull the slab into the gap, right. So, depending on two situations what we have, first one where we have isolated charge capacitor and we just place dielectric slab this way, how much force the slab will experience, and the second case is when the battery remains connected through the capacitor, how much force the slab will experience in that case. So, for two situations we have force x I am representing for the gap, right. So, this is x. So, when charge is constant, formula is minus du by dx when charge is constant, and when potential is constant, it is saying that this is at given charge and this one is at given potential. At given so at given potential we have this formula du by dx with plus sign, and when charge is constant the formula is minus du by dx, right. So, depending on the two situations we have, we either apply this formula or we apply this formula, right. So, let us see. So, let us first take when potential is constant, simplest case. So, when potential is constant, we know that potential constant formula is plus del U by del x at constant potential, right. Let us see. So, I want to find out the force on this slab. Procedure I already told you, I need to write the energy, potential energy associated with this one. I will differentiate that with respect to x and I will get the value of force, right. So, what is the potential energy associated? So, as you can see, there are two capacitors, one is which is filled with the dielectric, another which is filled with air. So, these two are connected in parallel, right. So, if I assume that this is a square plate, again the same way I am assuming it, a square plate of A by A. So, this is A and this way it is, right. Hope you can visualize diagram, right, in 3 dimension. This is A by A plate, right. So, upper plate A cross A, lower plate A cross A, and this distance is x. So, I can see two capacitor, one up to here, this combination, and another I can say this combination. So, this combination and this combination, right. So, and as the upper terminals are connected and lower terminals are connected, they are in parallel combination. I will try to write capacitance of this part and capacitance of this part. Let us see. So, capacitance of this part, if this is x, the remaining is A minus x, or here gap is considered as B and this we are considering as L, right, this as L, L or A, whatever you want to consider, right. So, this total is L, L by L plate instead of A by A, L by L, anything you can write. So, epsilon naught B, right, and into D so let us consider this as D and instead of a square plate I can also consider this as B and this as L. So, surface area will be B into L, okay, that way I am writing the expression. So, for this capacitor, epsilon naught B in bracket L minus x by D will be the capacitance of this one. Second one, as it is filled with dielectric of dielectric constant K, then I can write K epsilon naught B, this area will be B into x and this separation is D, I have written D here, right. So, I got capacitance of both the part. Now, if I have capacitance of this part and we know that these two are connected in parallel, then I can apply formula C is equal to C1 plus C2, right. C is equal to C1 plus C2. So, if I apply formula C is equal to C1 plus C2, then substitute the value of C1 here and the value of C2 here, then you will get this expression. You can see that this capacitance we are getting in terms of x, and when potential is constant, then we have formula potential is constant, then we need to differentiate this with respect to x, right, and then we will get force. So, differentiating this with respect to x will give me force. So, for that I need to write energy stored. Energy stored formula is half, you can use half q square by c, or you can use half cv square, or you can use half Q into V, right. So, out of 3 formulas, half Q square by C for energy, half CV square or half Q into V, I can apply this formula because potential is constant. It is easy to write. Capacitance I already have in form of X and potential is constant. So, here I am using half CV square, right. So, first let us get du. So, if u is written this way, u is equal to half CV square and I differentiate, then du by dx is 1 by 2 dc by dx into v square. Simple to write, right. So, we need to differentiate c with respect to x, as you can see. So, c, if I differentiate with respect to x, I will get k minus 1 because x to the power 1 will become 1. So, if I simplify, du is equal to, this is constant, dc, differentiate this one, you will get this one, divide by x both side, dc is what? dc by dx is what? K minus 1. I substitute this value over here. So, when I substitute this value over here, then I will get f is equal to du by dx epsilon naught b divided by 2d in bracket k minus 1 v square. As you can see that this force is independent of position. So, as long as some part is inside, the force slab experiences is independent of x. Some part is inside, force experienced is independent of so it is experiencing a constant force. This force is constant. This formula is not meant when it is completely fitting the gap between the plate, because force coming from both sides will balance each other and there will not be any net force. So, when it is not placed symmetrically, then only you can apply this formula, right. And do remember that field force is independent of the position. So, irrespective of the position of the slab, it will always experience constant force constant towards the gap, right. And if mass is given, then divide by mass, you will get the acceleration, and after you have acceleration, you can find out velocity, position as a function of time and all, right. So, today we have seen that what is the force experienced by the dielectric when it is placed inside a capacitor which remains connected with a cell or battery, right. So, tomorrow we will talk about the situation where once capacitor is charged, battery is removed, how much force dielectric experiences, right. So, I hope you understood today's class, right. Download the assignment and start solving, and most of the questions given in the assignment will be related to the involvement of dielectric in a circuit, right. So, whether dielectrics are inserted, dielectrics are removed, or such type of problem, you need to practice more, because these are the questions which are frequently asked in JEE, right. So, I hope you enjoyed today's class. This is it in today's session. So, thanks for watching.